is you want to identify what's the oldest material that I see, what's the youngest material that I see, what are the events that would have occurred, because when you start thinking about the relative sequence of events, you're really thinking in terms of processes. In the geologic sciences, particularly in structure, we're very, very interested in not just what happened, but what processes were active to give me the features that I see today. And so some of you have noted on your cards, wondering how we can determine the temperature. How can we determine whether or not we have a fault or a fracture? How do you build up this knowledge of what formation or what age of rocks you're looking at? And it really goes back to this. When you go out into the field, whether it's just on a road trip or whether you're doing detailed geologic mapping for some type of a publication for your research, the first thing we think about is just the relative sequence of events. And we have a series of tools that allow us to build a relative sequence of events. And if you remember, we've used those tools to a degree in trying to interpret some of these slides. So we use things like cross-cutting relationships. Now, who wants to summarize cross-cutting relationships for me? Tim?
That, and I might be wording it differently than it is in the book, that which cuts is always younger than that
Absolutely.
which cuts.
And so if we see a outcrop, let's say we go to an outcrop and we see something like this. So here we are standing at the outcrop. We'll put a hat on, a funny hat. Let's put a rock hammer in our hand. So we're looking at this particular outcrop and we see that, well gosh, this layer is cut and offset. We're going to call this a fault. And most of you who've had physical geology are going to say, well, that's likely a normal fault. But we use the principle of cross-cutting relationships. Since this fault cuts through those layers and offsets them, that fault must be younger than the layers that we see. If we make this a little bit more complicated, let's do something weird and have that. Which one is the youngest feature? This very topmost layer. This unconformity cuts across the fault, so the unconformity is younger than the fault. And then we deposited those layers. And so this takes advantage of also some other concepts beyond the concept of just simple cross-cutting relationships. We utilize the principle of initial continuity as well. Because when we think about deposition of sediments in a normal system, what we see is that the rock layers initially are fairly continuous. Now, they're not infinite, so they will change laterally, but that change is usually gradational, slow. In this particular case, this is a sharp change, and so we would not expect that to form in an actual system. So that's how we would apply the concept of initial continuity. We have the concept of superposition in here because you immediately said, well, gosh, this is probably the older rock layer, and that's the younger system as we go up steep.
That blue squiggly line, what was that supposed to
That was an unconformity.
Okay.
So that in this particular case, we can begin to piece together actually a relatively significant geologic story here in terms of looking at cross-cutting relationships, initial continuity, initial horizontality, even though I drew these as all being horizontal. If we change up the story a little bit, if we have something like this, can we piece this together? Who wants to take a stab at piecing that story together? Right.
The layers that are tilted now were deposited
Okay.
first.
Which one's the oldest?
The one, well, we can't really tell that, can we?
Well, relatively. Would I go 1, 2, 3, 4, or would I go 1, 2, 3, 4, or 1, 2, 4, 3?
Well, probably start from the left.
Okay, so we would go 1, 2, 3, 4. Then we have that feature, that's the unconformity. So that this would be 5, 6, and 7, right?
Okay.
How did we know that?
Because the bottom layers would have had to tilt before the top layers could be deposited horizontally.
So we start off with initial horizontality. We use cross-cutting relationships. We use continuity. We realize that this represents a time gap in our system where there was uplift, tilting, erosion, and then we deposit the younger, much younger systems here. Now, all of this is a relative sequence, and if we go back to some of the questions that have been asked, we've had questions about, well, how do you know what age those particular rocks are when you're in the field? If you just go out blindly into the field, most geologists can't just take a look at a rock and go, right, that's Eocene. Unless you've been working in the area for a long time. And so, since I'm old and have worked in a lot of different areas for a very long time, a lot of times I can guess and be reasonably okay that these are Eocene, these rocks look like they're Cretaceous, those rocks look like they're Precambrian. One of the things that we look at is we look at the relationships, but we also begin to think about them in terms of fossil content. And we use the concept of faunal succession, so that when we think about trying to establish a relative age for rocks, we use the concept of faunal succession. Faunal succession is relatively simple in its statement, but incredibly sophisticated in its application. Steve?
Did you say funnel?
Faunal succession.
Font with the O or U? Oh, funnel.
Okay, faunal succession. What you're looking at is a way of determining relative age based on fossil content. The more detailed you can get into the fossil system, the more accurate you can actually become in determining an age date. And so if we look at a simple example, some of the ideas regarding faunal succession is that life forms have become more complex through time. If we go back on our geologic time scale, if we had a time machine, that would just be wonderful. If we had a time machine and we could walk over here and say, okay, I want to be in the Stenian. And then poof, magically this room is sort of like Miss Marple. This room would be taken back to the Stenian. We could open the doors, all parts of the building would be gone and would be in the Stenian. Would we find any fossils? Not really. You would have only the most archaic, odd, single-cell things that may be viral, and nothing else. So if we were to fast forward and say, well, I want to be, put your coats on, I want to be in the cryogenian. And then back slowly to just the beginning of the cryogenian, what would we have seen in terms of organisms? Still very, very primitive. If we move up to the beginning of the Cambrian, what would we see? Well, we start seeing shelled organisms. We start seeing brachiopods. We start seeing trilobites. We start seeing more complex organisms that have an exoskeleton. And so if we start examining these rocks and I start seeing trilobites, I know this is not Precambrian. And I also know that trilobites were present up through Permian, and then they became extinct. So these rocks would be somewhere between Cambrian and Permian. We've narrowed it down quite a bit, but that's still a huge block of time. So we'd start thinking about, well, what other organisms do I see? Do I see any fishes? Do I see any vertebrates? What type, what species of trilobite am I looking at? Or if I'm seeing brachiopods, what species of brachiopod am I looking for? Because individual ranges of those fossils typically are 2 million years or less in duration. And so you can begin to narrow down by looking for specific species that you're aware of or different ranges of species. And so if I have, and I'm going to draw something that looks funny, but if I have a series of data that have different ranges for the fossils, so that I have here, this is our first occurrence known of that particular fossil, this is the extinction event. So now if I look, and if I have all those above, my range in time is really quite narrow. That's my range in time that I can affix for those rocks. And so I can use this idea of organic evolution and faunal succession to narrow down my age range, if I'm relatively comfortable identifying specific fossils. And so as an example, some of the work students have done with me down in the Arbuckle Mountains depends on their being able to identify a range of lower diaphalasma brachiopod. So they have to be able to recognize the difference between upper diaphalasma and lower diaphalasma, which of course is obvious because they come with labels in the field, right? So they have to be able to identify those particular brachiopods fairly accurately. Or if we're in the Silurian and Devonian, we have to be able to really look carefully at the brachiopods and tell right where that Silurian Devonian boundary is exposed in a rather monotonous rock section. So that we can use faunal succession, because we know once an organism is extinct, it does not come back. So that once the trilobites were extinct, we can't go out fishing for trilobites right now. That's kind of a shame. But it's also to be a good thing. If we had velociraptors reappear on campus, it would make getting between classes a little bit more challenging. So we're kind of happy that faunal succession works and that extinction events are permanent. So does that explain? So that when we use this, we start off with just what's our relative sequence of events, and then we begin to refine down. And so as you build experience as a geologist, when you're out in the field and you're out mapping, you have all of these things in the back of your head, and you're starting to learn how to identify different periods based on the lithostratigraphic changes, the color changes. For example, the Dakota sandstone, which is a wonderful Cretaceous marker throughout the western U.S., you can recognize the Dakota just within seconds. You can be driving down the interstate at 75 plus miles an hour and just glance it out of the corner of your eye and go, boom, that's Dakota. I know I'm in the Cretaceous system. And so you build up this expertise over time. And all of you can do this. So we wanted to think about relative sequence of events, Younging direction, because when we look at a system, we want to know in rock layers what direction up initially was. And so we rely on a range of primary depositional features. Things like mud cracks, things like ripple marks, things like cross-bedding that can help us determine depositionally at the time of deposition which direction was up. Because things can get rather strange. And I talked briefly about an example from a field camp that I taught where what we had, and I'll draw the whole system out, but then I'll modify it a little bit. We had a series of rock layers, 1, 2, 3, 4, 5, 6, I need another one, 7. And now what we ended up doing is that each one of these was nearly vertical in the field. It would stand up in relief. So in the field, over an area that was roughly, this would have been roughly 3 kilometers across, you see these 7 different quartzites. All of them roughly uniform in size. They seem to be similar in terms of their color, in terms of their textures. And in between them, you had a second sillimanite schist. So you knew you were at relatively high-grade metamorphic conditions. But the question comes up, am I looking at 7 distinct episodes of sand deposition within the depositional environment that was subsequently metamorphosed? Or am I looking at only one layer that has been folded dramatically? And so when you look at that, determining Younging direction becomes critical, because that changes your entire interpretation. Are you looking at just 7 unique layers versus 1 layer folded? Huge, huge difference in your interpretation. And so what we had to do is look at fine cross beds that were formed when the sand was deposited and told us which way up was. And so what we found was that if I add some arrows, this was up, that was up. So this was up, that was up. This was up over here, and that was up there. And so it told me that, or told us as a group, that the Younging direction was changing uniformly across the area. And so it best fit a model of folding. Because if I think about this system, I have this, remember, and so I would expect always to have Younging direction doing this across those folds as I've been the layer. And so just a fundamental knowledge of Younging direction and these cross-cutting relationships allowed us to determine what we were doing in that particular system. So very, very simple, very straightforward, but something that we want to carry. Now, we've discussed very briefly time scale. If you look at your evolution of the time scale handout, that 11 by 17 sheet, time scale, relative sequence of events, is something that geologists have worried about, thought about for a very long time. It goes all the way back to Argerino, some of the early Italian geologists, some of the early geologists in the Alpine system, trying to piece together the story and asking themselves, well, which of these rocks are oldest? Which of these rocks are youngest? And can we begin to understand the events that have occurred here to give us this rock system? And so that's a question that all geologists are asking. And so they began with a very, very early primitive time scale where you just had a primitive, then younger, younger, younger. That was adopted with those weird German-sounding names in Europe. And so you had rather strange names like Urgebirge, Angeschimtgebirge, Neues Glücksgebirge. Those were describing relative ages. The Urgebirge were the oldest, the primitive rocks, the crystal rocks. And as we went on up, this idea began to expand through Europe into Britain, and we started trying to refine. And the initial names were actually named after specific lithostratigraphic sequences. And so Cambrian was named for the Cambros region. And then they found rocks underneath it, and so they did the intelligent thing and said, oh, that's pre-Cambrian. And then on up, so that we developed a working document for a time scale that is governed by the International Commission on Stratigraphy. Each continent has its own stratigraphic commission, and its own nomenclature. Now, those of you who take the History of the Biosphere class with Dr. Scott, you may or may not know, he may or may not tell you, he has chaired the North American Commission on Stratigraphic Nomenclature. He's a member of that commission. And so he helps decide where these boundaries are. And so some of the boundaries, if you look at the time scale that we have in the course modules, so if we look just a second at this particular time scale, oh, did they goof it up again? These guys. They need to be messing with this monitor. Screen resolution. We want to go down to really around there. Apply that, say okay. Keep changes?
Yeah.
Does that work? Is that looking okay? All right. So if we look at this time scale, see these pins all along with those little nails, all along the edge here. These are a notation that internationally we have identified one outcrop in the world as the perfect place to look at that time period. So at that boundary between that epoch and that epoch, we have a locality where we can go, everyone can examine the fossil content, the stratigraphy, and agree that that is a particular boundary. So if you're interested in the extinction event that occurred at the end of the Mesozoic, there's a locality where you can go and put your finger and say, that is the boundary between the Cretaceous and the Paleocene. Which is kind of a cool thing, to be able to touch that boundary. That is called the GSSP. That is a standard. They publish a paper on that. And so if we look at the introductory materials, now you've been ambushed by a homework assignment who crept up behind you when you were taking your quiz. And so the homework assignment down here is to take one of these GSSPs, and I have the GSSP table, and what I want you to do is, let's take a look at this assignment. Number one, we want to download for your personal computer the most recent version of a program called Timescale Creator. It's a wonderful little program, works on Mac, works on Linux, works on Windows. It's very, very easy to use. Once you put that onto your computer, it's a safe download, so don't need to worry about it. If you go to this particular site, it's guaranteed to be a safe download. And then I want you to generate a small time range, time scale, in a time frame of your interest. Something that you haven't looked at before. And include the standard chronostratigraphy, regional stages, geomagnetism, any fossil data that you can find. Yeah?
How big or small is the time scale range?
Well, it's going to depend on what time range you're in. If you pick just the Miocene, that's a fairly short time frame.
Okay.
But if you pick from, let's say, Cameron Ordovician boundary up to Pennsylvanian boundary, that's a nice time range that would have lots of exciting events going on. A global reconstruction using the Blakey reconstructions and any other data that you find interesting. Export those as a PDF file that you're going to upload to Harvey. Explain what the results mean. Tell me what this thing is trying to tell us about in terms of the geologic history of the Earth. Upload that as a Word document. Take your GSSP table that I just pointed out. Find the paper that describes that particular GSSP, that standard. And it's got to be one you haven't worked on before, so if you've been working on the Albian-Semanian system, don't do that one. Choose a different one. If you've done something before, choose a different one. Read that paper, and then write a paragraph explaining, in your own words, why that particular locality was chosen. Why not some other locality? And what's the significance of that particular thing? So, you have deliverables on there. Email me if you have any questions or problems, because I hope, the intent anyway, is to help you realize that the time scale really is a living document. It is something that we're working on as a geological community, and it's the basis for which geologists communicate.
Okay, are you saying that we pick something on here where there's a pin?
Right.
Okay, so we don't pick anywhere where there's not a pin for
Correct.
this homework assignment?
It has to be in the GSSP table,
Okay.
and that GSSP table is in your notes section. So that is a homework assignment for you to start working on over the weekend. I hate to be bored over the weekend. What's worse than having the weekend with nothing to do? So start working on that. It's due next Friday. Okay, and we will also have a homework assignment that will appear next Friday as well. I love homework. So that gets us through evolution of the time scale. We need to chat briefly about radiometric dating and about deep time, because what helps us really affix the absolute time is the concept of radiometric dating. And so, if you will, let's just go up and take a look at the concept of deep time, and let's zoom into, are you going to misbehave like this? Let's just quickly go through some of these. And make sure we understand. So if we take a look at this one, can you tell me which one of these features is younger?
Younger?
Younger. Is it this or is it that? It's got to be this because it cuts across. This is the Pikes Peak granite cutting across the Boulder granite. Here we have a fault and a fold. Do you see anything else? Something right there, right? There's something odd right here. That's a fault. That's the Amsden fault. These rock layers are tilted differently. These come in, bend over, and terminate right there. So we can get a handle on this relative sequence of events so that we're relatively comfortable with these. We're comfortable with unconformities, nonconformities in a system, angular unconformities. Here's a beautiful angular unconformity from the Arbuckles. And what we're looking at here, these rocks down here are Ordovician in age. These rocks up here are Pennsylvanian in age. So we have deposition of this pile, tilting, erosion, and then deposition again, and we finally have a fault that cuts it right there. Now, the intriguing thing is if you look at younging direction, this is actually upside down. That's up in that system. So we have a pretty good handle of how do we do that. This is a beautiful angular uniformity near Socorro, Mexico. Absolutely gorgeous thing. I was in a rental car, and they were not terribly happy, but the bumper and the muffler were in the trunk when it was returned, because it was just too good a thing to miss. You couldn't. This was about 2 miles off road. It wasn't a public drive, unfortunately, but the car sort of survived. So what we're doing when we're looking at radioactive decay, and the best way to do it is just to look at that. Certain atomic nuclei are not stable, and they will begin to decay. And the decay process is simply controlled by this. You can take a proton and a beta particle and generate a neutron. You can take a neutron and it can decay into a proton and a beta particle. These nuclei are actually shielded rather amazingly from outside pressure temperature effects by the electron cloud. The vast majority of what we consider to be solid matter is really empty space. When you do a scale, the nucleus is this tiny little thing in this vast empty space. And so we really can't influence it by temperature or by pressure. We can't cause it to emit faster or slower. But we use this to come up with a decay curve. And so if we look at a normal decay curve, this would be a typical decay curve. We start off with 100% of the parent material, and for each half-life, we end up with half of the parent material remaining. So if we go from here to here, we have another half, another half, another half, so that we have this asymptotic, beautiful exponential decay curve. You can express this as an integral. I chose a simpler form for this particular system. And we can use the ratio of daughter to parent material, understand how many half-lives we are, try to put that in terms of what the decay path really looks like in a system. And I have here a decay path. This is the U-238 decay path. And so you have steps here of alpha particle emissions, beta particles. So we have alpha step, beta, beta, alpha, 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 alpha. We diverge here, we can diverge there. And then I have the half-life for those steps. And so you can work out very, very nicely to an amazing degree of accuracy what the absolute age of a material is, depending on what materials you have present at the beginning. And so the most common materials that we use are zircons, micas, hornblends. In here, we have some wood and charcoal that we can use on carbon and nitrogen dating. We have to be a little bit careful in that range, but there are ways to tie this down very, very effectively, and the relative time range that they're good at dating. So radiometric decay helps us affix a particular time, and on your time scale, those ages that have a clock by them, a little bitty clock, have been determined radiometrically. So this is how we get an idea of relative age dating, absolute age dating, and the concept of peak time. Because when you're a geologist, when you're out in the real world, and you can never get away from geology, that's one of the wonderful things about geology, is you're traveling in time, mentally. You're thinking about what happened in this region over geologic time. Okay? So on Monday, if there aren't any questions regarding this week of introductory materials, we're going to start on fractures and fracture systems. Read the first small bit of chapter 7 in your text so that we can begin thinking about what fractures are, how they behave, what are the geometries that we see, and begin piecing together when we see a structure, what happened? Okay? All right, have a great weekend.
No, that goes.
Oh, really?
Here's my-